Good afternoon and welcome to IFC Webinars. I'm your host, Richard Miller from IFC. On today's event, Low Frequency Alarm Signaling Effectiveness. And this is a continuing series of a four-part presentation presented by the Fire Life Safety Section in collaboration with the National Home Builders as part of an informational gathering process for a symposium at Community Risk Reduction Conference. Today's webinar is being broadcast by using voice over internet protocol technology through your computer, speakers, or headsets. Please make sure that your speakers and headsets are turned on and the volume is turned up. Audience microphones have been muted. If you're having any difficulties with this, please contact IFC support at webinars@ifc.org or via the chat function. And again, we'll be monitoring the chat function today in case you run into any difficulties, so we can try to help you out right away to make your experience more delightful. The chat, Q&A, and handouts are available at the top right of your screen. Please use the chat area to go ahead and introduce yourself. Let us know who you are and where you're from and what your interests are, as that'll help us better serve you with information for the presentation. If you use the Q&A function, please type in your questions. You can pre-type your questions if you want, and we will go through them. And if we can answer them throughout the presentation, we will, but we'll go over them all at the end when your presenter is available and complete with today's presentation. I'd like to talk a little bit about some upcoming events. Fire Rescue Med starts April 30th through May 1st in Las Vegas, Nevada this year. The Community Risk Reduction Leadership Conference, May 14th through the 16th in Glendale. As part of that conference, the Low Frequency Alarm Committee group with IFC, Fire Life Safety Section, and National Home Builders, and a whole bunch of other great organizations around the U.S. are gathering to look at this information that's presented and look at this overall problem. So it'll be a two-day event starting on the 13th and a half day on the 14th before the conference opens midday. The International Hazardous Materials Response Team Conference, June 5th through 9th in Baltimore. Again, another great event for all the hazmat personnel around the United States, and lots of great stuff occurs there. And then Fire Rescue International this year is in Dallas, August 14th through the 16th. So please go to ifc.org and join in on conferences and pick the one that best helps you in your career. Today's presenter is Josh Dinneberg, and Josh is part of the symposium group that's helping us work on this project, is a mechanical engineer with 19 years of experience. He is the fire test specialist for CSA Group with a primary focus on fire hazards of emergency storage systems, including design and operations of a fire test laboratory used for testing and certification of lithium-ion battery energy storage systems. Mr. Dinneberg has designed and developed and implemented a variety of research testing programs in fire detection, signaling, and suppressions, including evaluation of fire hazards for electrical equipment, energy storage systems, flammable liquids commodities, residential cooking, wildfire, and 3D printed materials. Other test programs have included analytics and full-scale evaluation of aspiration of smoke detection, beam smoke detection, video smoke and flame detection, optical flame detection, and low-frequency alarm signaling effectiveness. Josh has authorized the updates to the 2021 edition of the NFPA Fire Protection Handbook for Section 2, Chapter 6, Fundamentals of Fire Detection, and Section 14, Chapter 2, Automatic Fire Detection. He has also authored the updates for the 6th edition to the SFPE Handbook of Chapter 78, Data for Engineering Analysis. And it's my pleasure today, as we move forward, to introduce Josh and let him talk for the next hour or so as we move through this great presentation. Josh, over to you, sir.
All right, thank you so much. Hopefully it's a little less than an hour or so. We'll try to keep it under that for sure. So as we mentioned, this whole series has been on kind of low frequency alarms, how they've been proliferated in the codes, some of the manufacturers and their devices and what they can make. And mostly my focus here is on the effectiveness of that signal and discussing a lot of the research and the history of the codes that went into where we sort of stand today. I did want to mention here, this is part of this low frequency alarm symposium happening as part of the community risk reduction meeting in Arizona. So if anybody would be attending there, happy to chat and discuss. So my work in this area is mostly focused as a result of a National Fire Protection Association Research Foundation report. So this was a literature review I did in 2020 with the support of the foundation and a number of their sponsors. I didn't actually do any of the laboratory work. I just read a lot of stuff and synthesized it and put it together. We did have Dorothy Bruck on our panel as an advisor for that as well. And she did physically most of the testing that brought us a lot of this low frequency alarm. So we weren't sort of doing this in a vacuum, but I got to read a lot and write a lot, develop my area of expertise in here. I highly advise you to download this report. It is a real page turner, about 130 pages with about 125 sources in it. Really keep you up late at night reading that one. But I tried to be really comprehensive in what do we know and how do we know it and what can we do with that information. So I just do want to throw the disclaimer out here. When I did this research 4 years ago, I was a research engineer with Jensen Hughes. I'd been there about 15 years. So I did that work through them. I'm now the fire test specialist with CSA Group. So I didn't do any of this research affiliated with CSA at the time. So I did want to throw the disclaimer on here that everything I'm about to say is just me. It's not Jensen Hughes or CSA or NFPA or the Research Foundation telling you any of my conclusions and opinions. So the Research Foundation started with this kind of defined problem. Back in 2019, 2020, we had a number of tests and research data showing that there was increased waking effectiveness for this low frequency alarm signal. It even had been required for sleeping areas, for notification appliances, and also for sleeping areas for the hard of hearing. But that had not proliferated down to all the occupancies and all the occupants. So it was pretty limited to those areas. A lot of that was based on the limitations of technology. So smoke alarms are intended to be pretty low power. Big push in the last couple decades was to have sealed 10-year batteries on smoke alarms. So we would take away the ability of occupants and residents to disable their alarms, and we take away their need to be replacing the batteries to maintain effectiveness. This made it really difficult to incorporate these low frequency alarms into single and multiple station devices, specifically that would run off of battery power. Part of this trouble was the requirement for alarm devices to produce 85 decibels at this 10-foot distance. This is a pretty high level of sound, and it's required of all these devices. So the question NFPA Research Foundation wanted answered is, can we reduce the sound pressure levels required for the low frequency alarms from that 85 dBA? So it's a little quieter, it draws less power, it's more able to operate on a battery. And can we do that and still actually provide our waking effectiveness, still wake up at least equal to the amount of people we wake up now with the 85 dBA alarms, and ideally more people. So this is sort of the question we started with as the basis for this research. So there's a few issues here, like critical questions we had to answer as part of this. So what is the basis for the existing requirements, and what justification was there for why they became the requirements? Why is it 85 dBA? Why are the alarms have to be this? Why did this proliferate into installation codes and standards? And what data was used to justify all that in the first place? what is sort of our baseline expected performance from existing high frequency smoke alarms? So if we have to be better or at least equal and be quieter, what is that level of performance we're expecting? We all know it's not 100%. Everyone doesn't always wake up to every time an alarm goes off in their house. There's some baseline level of expectation there. What evidence do we have for the efficacy of the low frequency harmonic tone compared to that baseline? So how do we numerically and in a quantified way compare what that low frequency tone does to the high frequency tone? And can we make assessments about that? And then a more fundamental and less quantified question, why does that alarm work better than a high frequency alarm tone at waking up people who are asleep? What is the physical basis behind that? Is there any explanation we can understand about why? So I did want to play a couple of the tones here just so everybody has some experience with them. I'll start with that high frequency tone everybody's probably heard and is probably familiar with in their home. Sorry, you can hear my mouse clicking playing that. But everybody's probably heard that tone before. It's pretty high. It's got that temporal 3 beep to it, you know, beep, beep, beep. Everybody's probably familiar with that. And everybody's probably not familiar with the lower frequency tone. Oh, I think I just did something. Sorry. Did I hit the wrong button here? I went backwards. There we go. Okay. So it doesn't sound quite too different, but you can definitely tell it's a much lower tone. It's actually a fuller tone as well. It might not come across in the computer sound, but it's got additional harmonics added into it. That's why I'm calling it the low frequency harmonic tone here. It's not just a lower frequency. It also has some additional built-in harmonic tones to make that sound a little richer and fuller. Whereas that old tone that comes out of the piezoelectric transducer is usually pretty centered at about one frequency, one tone. So trying to quantify this problem gets really, really difficult. So I did want to work on some of the critical understanding fundamentals. I think having a good discussion about this and an understanding moving forward sadly requires a lot of understanding about the basics, which can be pretty complicated. Just the production of sound and how people hear it, how people sleep, and then how to wake people up when they're asleep, and how to interpret research and test studies that wake people up and compare them between each other. So just the basics of sound, it's just a wave of pressure fluctuations. The air bounces, it moves as a wave, it bounces off of surfaces, and it creates pressure. Your ear, picks up that pressure wave and interprets it to your brain. This is usually rated in decibels. The decibels are just a logarithmic scale. It's relative. It's based on that minimum audible level of a pressure you can hear. It is also based on the square of the sound pressure, which is proportional to the power, the actual physical raw power of the wave. So we actually rate these in some different scales. The one you'll usually see is dBA. That is the way smoke alarms are currently required to be tested for their audibility. You can see they have slightly different ratios compared to just the raw decibels, which is the power. If you look at dBA, it actually slopes down pretty far here at these lower frequencies, which basically means you get a penalty at those lower frequencies to have the same A rating as the raw decibel rating. I really only bring this up because if you look comparing 520 hertz, the low tone, and about 3200 hertz, that high tone, you see there's a punishment for the lower frequency of about 4 decibels. So it needs to be 4 decibels louder to get the same A rating for the low frequency tone as the high frequency tone. This gets really important really fast because of that logarithmic nature of the decibels. 3 decibels is twice the sound power. So this is almost 3 times the amount of power required to make the same dBA rating, the 85 dBA as it's measured for the alarm performance as a high frequency tone. So one of the reasons this really comes into question is the A rating is based on the limits of hearing. So what humans hear at really, really low levels, about 40 decibels, the quietest sounds that they're able to pick up, this is where that A rating impacts as a function of frequency. The B and C ratings are actually meant for much louder signals up to 60, 70 decibels. And they weight those low frequencies as with a stronger component than the A rating. So there's a question here about if the A rating is really appropriate for alarm signals, which are based at 70 to 75 to 80 decibels, when the A rating is really meant for about 40 decibels. So maybe we're really punishing this 520 hertz signal, making it have that same A rating, but maybe that's why it's more effective at the same A rating, because we're essentially punishing it and requiring more power. So human sleep, even more complicated than hearing and sound. We sleep in these cycles. So basically you go through a series of cycles of low, kind of light sleep. They call this fast wave sleep, and kind of deep sleep, this slow wave sleep. The wave there is your actual delta brain waves. They measure this with an EEG. So a lot of these original, very early sleeping studies would try to wake people up in different stages of their sleep cycle. You can see this graph kind of here up in the upper right. You're looking at how loud something needs to be to wake somebody up. And then over the course of the night, you kind of start in very deep sleep. It gets a little lighter and you go up and down through these cycles. It actually takes less and less sound later in the night to wake most people. The actual comparison here is done with people who called themselves deep sleepers, people who call themselves light sleepers. So there's a pretty big difference there in the sound meant to wake them up as well. But you do go through these cycles through the night. So if you're not measuring these things when you try to wake people up in a study, you can get some very, very different results that aren't due to the effectiveness of the alarm or the way you ran your test, but just because somebody's in a different cycle of sleep, they woke up easier this one time. So this gets pretty complicated in testing. We also find that there's a correlation here between age and these cycles. Children have a lot of that slow wave sleep, very deep sleep. They're very difficult to awaken, and alarm testing studies have found that. Older adults have a lot less of that deep shortwave sleep, but they're also harder to awaken because they can be less sensitive to sounds. So it was proposed a long time ago, back in the 70s, that when you're asleep in this light sleep, this fast wave sleep, that's related to dBA, the way you interpret sound. But when you're in shortwave sleep and you're really deep and you're really asleep, that's much more related to the raw power, the decibels. So just another statement there that maybe that dBA is missing something in the way we're testing, reporting, and measuring the sound for alarms. There's also about a million different confounding factors that make comparing all of the studies that have been done on waking really difficult. So just one thing to keep in mind here, this audible alarm threshold, I'll probably throw that acronym around a little bit. That's how much sound in the dBA at which a test subject responded. And generally for our purposes, that means they woke up. So all these studies have a lot of different tones and pitches. Their harmonic tones, their pure wave tones. A lot of early studies just used like 1,000 hertz tone because it was simplistic and well-rounded, and is kind of the middle range of what you can hear. Other studies have used white noise, which has this really broadband frequency tone. Studies have used speech or instructions, or even a recording of your mother, male and female voices, or even tests with fire cues, like a crackling wood sound or a pop or explosion. All of those different signals can get some pretty different results. We don't just get to say, 70 dBA always wakes people up. How it's presented to people really matters too. Does it keep getting slowly louder until they wake up? Do we give them one sound? Does it say steady? Does it beep? Does it shut off for 10 minutes and then come back on to see what they'll do? Does it shut off for 4 hours? Do we use speakers? Do we put headphones in somebody's ears? Do we use real smoke alarms? All of those things really matter to the outcome of the test results. All of the ages and genders of the test participants, whether they have normal hearing or they have a hearing impairment. Is their hearing impairment been measured by a standardized test, or is it just someone signing the form that says, oh, and I have a hearing impairment? Did we measure their sleep cycle at the time we gave them the alarm, or did we not? How early in the night did we give it to them? Have they been intoxicated, or are they a regular user of intoxicants? Do they have any other form of mental illness, depression? Are they light, heavy sleepers? Do they have insomnia or narcolepsy? Do they use CPAP machines? There's a million other confounding variables here. Did we tell them ahead of time that what you're here for is an alarm and we're trying to wake you up? Did we surprise them with it? Did we play the alarm for them ahead of time, or have they never heard the alarm sound? Do we test them in their home? Do we test them in a lab? Is it a fake home built in a lab? Do we control the ambient noise? Do they have an air conditioner or a fan running? How do we determine if they woke up? Do we watch just their brain waves? Do we make them push a button? Do we make them get up and make a phone call to the test operators to say, hey, I woke up and I heard this? All of those have a pretty big difference in what we call awakening someone. And then how long did we do this? Did it one night in the lab, or did we put an alarm in their house and surprise them 2 months later when we set it off and tested that? So there's a million different problems in all of these studies to come up with a quantified number for comparing them. So I do want to give a not so brief history of alarm signaling here. What I found to be a pretty critical factor in this is, how did the standards develop to where they are now? Why do we require what we require out of these? And how were the codes and standards built over time to get us where we are now? Because if we're going to change them, we should understand really why they are what they are. So I'm going to take you all the way back into the glorious 1920s here. At the very start of our building exits code. Let me catch up on my slides over here. So basically in the 20s, we said we really need a distinctive signal and we need to standardize it for fire alarms. So naturally, 40 years later, we came up NFPA 74 and said it's got to be audible everywhere. And all of the devices need to be rated at this 85 decibels at 10 feet. Notice that one there is decibels. It's not in that A-rated decibels. If you look at 1974, that became A-rated decibels. So there's this constant understanding of research technology, the codes and the standards, and they kind of cycle around each other. Changing that in 1974, people were doing all these waking studies. They were starting to use dBA ratings. And so they applied this into the standards then. So a little more background. Pull this here. So 1975, NFPA 72A is giving us that 3-pulse temporal pattern. They're giving a description in the appendix. There was a lot of debate there in 1975, and I highly advise you to either read kind of what I have in the full paper or go back to even some of those meeting minutes, it sounded like quite a lively conference discussing all of this. A lot of people came in with proposals, slow whooping sounds, dot dot dash pattern, which is the Morse code of F for fire. But basically, we were starting to see these low power piezo devices coming into the smoke alarms, and the tones that it would make were not standardized, but accepted. And if the feeling was that there was no reason to really standardize the tone, as long as we standardize the pattern, we can let people make different devices for different environments, right? If they wanted in an industrial plant where a certain frequency may not be audible. So in the end, really that tone was just kind of accepted. And in 1976 is when we got UL 217, 85 dBA at 10 feet for all those smoke alarms. Basically, at this time, a lot of alarm researchers started questioning if even that was enough, and does this work, and starting to do waking experiments. Is it loud enough through a hallway, which is how they were being installed back then? And a lot of waking experiments were based on effectiveness of 50%. That was what it meant to wake people up in a test. And is that really enough for life safety? So now we got the 1980s. We're starting to think about, okay, I think we really need these things in a bedroom. So there was actually the first study, not until 1980, where we actually were testing audibility and waking for actual smoke alarms. Every other test up till that point had really only focused on just audible tones and how loud does it need to be to wake somebody up, but not really in any fire alarm context. So this was a study by Nober and a group of researchers. They did this through NBS, now NIST. And they used 30 college men and women, and they all woke up at 70 dBA over an air conditioning unit. This basically became the basis for all the 70 to 75 dBA requirements that came into building codes over the next years. It looked effective in this test. Everyone agreed. All these college kids woke up. We're good. Let's go. Here's the standard. Some other people started looking at this, and we're not getting this 100% response. Children weren't waking up to anything. People taking sleeping medication were only waking up about half the time. And even the normal populations being tested, other than these 30 college students, were really not waking up 100% of the time. But really, despite all these concerns, kind of this 70 dBA number started to make its way out into all of the code standards and requirements. So one interesting thing that did get added here in 1980, at the time, we're really only putting alarms in hallways. It's the only place they were really required. But NFPA 74 did recognize that if it's going in the bedroom, it doesn't really have to get through a door. So there was an allowance made to let the devices be 75 instead of 85 dBA. So be a little quieter. It's going right in the bedroom. This should still be fine. And we get our first kind of building code from the British standard recommending 75 dBA at the bed. So as long as the device, whatever the device does, if we're getting 75 dBA at the bed, we should be good. We feel confident. We also, end of the 80s, finally get our interconnection of alarms for new construction. I would say a very, very good addition. So now in the 90s, if anybody's familiar with how building codes worked back then, there were all kinds of regional building codes in addition to the national ones. And they all started bringing in some of these requirements. So we get Boca bringing in a 70 dBA with this 15 above ambient, 5 above the maximum. We're getting 70 dBA is really, really, really based on some recommendations that you lose about 15 decibels going through a door. So if you got 85 in the hallway, you'll get 70 in the bedroom. So kind of tying together the installation standard with the device standards. You're starting to see this as well in the Southern Building Conference codes and standards a little later in the year. So we keep moving through the 90s. We're starting to get a little bit of harmonization. NFPA 72 starts to bring these same requirements in. You still got 85 dBA 10 feet. Brings in all the 74 and 72G requirements. You get interconnection. 93 is when we get this first time every bedroom in new construction. And it does follow that same 70 dBA requirement. 95, it's where we actually get an official requirement for that T3 pattern we played before, you're probably familiar with. And the Canadians kind of follow the British and go 75 dBA at the pillow. So the US is kind of looking at 70. International is kind of looking at 75. They're requiring a little louder for installation standards. So end of 99, we're starting to look at 2000s. You get this great event where the International Code Council creates the IBC and consolidates all these different building codes, but they don't really change any of the requirements here. We're still looking at 70 dBA. 72 at this time gets rid of that exception that used to exist. So devices that went in a bedroom used to be able to be allowed to be 75 instead of 85 dBA. But this requirement goes away in 1999. Now, I wasn't there. Some of you probably were. I'm just a little too young to have been involved at this time. But my belief is that this is because of the complication of having different listed devices. So if you ask installers or the general population, and they go to the store and there's 4 bedrooms only and 4 not bedrooms devices, there's really nothing stopping them from putting the wrong ones in the wrong places. So I think just getting rid of some of this complication there is sort of the reason that this went away. But in theory, those devices would still be compliant with the requirements for how loud these should be at the bedroom. Oh, sorry. I don't know that I moved that one. Sorry, I'm right here, skipping through the wrong ones. So you can see here, 2000 ICC, 1999 NFPA removing that exception. So 2000s, now we're starting to harmonize all these requirements. We're starting to really bring together these codes and standards. Let me jump back. More. Okay, so now in 2000, 2010, it's when we really started noticing, are we sure that these alarms are actually working for everybody? We started identifying all of these at-risk groups. I want to give a ton of credit on this to Dorothy Bruck from Victoria University. She did the bulk of the studies that have brought low-frequency alarms into our codes and standards and really raised the awareness of this at-risk problem we were having with existing alarms. So children were not waking up. People who were hard of hearing were not waking up. Older adults were not waking up. People who had consumed alcohol or other sleeping aids or other intoxicants were not waking up. You can see this chart over here is actually a 2004 study done by Bruck. You can see this middle column being much higher. That's the high frequency alarm tone that we played before. And you can see it requires a significant amount of more sound than speech, which is the dark blue, or the low pitch tone we're talking about. So this was done for people consuming alcohol. You can see how much it jumps for all the alarm types, even with a legal to drive blood alcohol content. We get a significant increase in the amount of sound required to wake people up. But you can see how much less sound is required in all of these scenarios for that low frequency tone. So this is one of the first times we really started seeing this in studies, that tone was working much, much better. The study below is for children. You can kind of see where the orange is they did not wake and the blue is the number of people who did wake. So you can actually see the standard signal has that really long orange bar here. A lot of these children did not wake up when they were being presented with that. but that went way, way down when being presented with the low frequency T3 alarm. So we're starting to see here for a couple of at-risk groups, there's a pretty major impact in waking people up at lower sound pressures. So this continued. Some more studies were picked up by other groups. This was done by Combustion Science Engineering. This top right section up here, this was based on seeing what people who were hard of hearing would respond to, including people who were reported as fully deaf. So the high frequency alarm, you can see among the normal hearing group, you're getting 92% of them were waking up to that and 100% at the low frequency. So not too big of a difference there. Among the normal population, we're getting waking. Once we go to the hard of hearing group, we're down to 57% for the high frequency alarm and 92% for that low frequency. So there was a real clear impact there. Like, okay, among this hard of hearing group, we are definitely waking up a lot more people. So we'd seen it in people consuming alcohol, we'd seen it in children, and now we're seeing it again for the hard of hearing. People who were reported as deaf, even 11% of them woke up to that low frequency alarm, and none of them to the high frequency. Some additional studies were done here by Dot Bruck at Victoria University, comparing that low frequency tone that she had tested a few times with a range of different tones. Maybe we didn't, strike magic with the low frequency tone. Maybe just the high frequency tone is objectively terrible. So she did a bunch of tests here with different frequency harmonics, some whooping tones, some pure tones of a range of different frequencies. And that 520 hertz harmonic tone still ended up getting people to wake up at the lowest sound pressure among that group. So good happenstance. She seemed to have found the best one first, but it did turn out that seems to be among the best signals for these groups. So a lot of the way I wanted to compare this data for these studies was looking at how often did people wake in a number of studies, like how confident will we be that someone will awake at a given sound pressure level. So you look at this chart down here. Down here is the sound pressure level in decibels. So it gets louder and louder as we move to the right. If you look vertically, that's more and more people waking up. So if you play this really quiet tone, you get 30% of people to wake up. You get louder and louder. You get more people to wake up until you approach 100% of people waking up at the loudest possible tones. So one of the ways I was looking at this data, this had all been sort of summarized really well by Dot Bruck in 2010, is what does it take to be equivalent? So if we're looking at 75 dBA, that's what we're requiring at pillows and beds. How many people wake up with the standard high tone alarm? And if we go backwards to the left, how loud does it need to be for that high frequency alarm to get the same amount of people to wake up? So how much quieter could we get and still get that equivalent effectiveness? So if you look at that table up in the upper right, among these at-risk groups, older adults, people with hearing loss, people consuming alcohol, and even a not at-risk group, just sober young adults, 18 to 26 years old, you can see we're anywhere from 10 to 20 decibels of equivalent performance. We could be quieter by 10 to 20 decibels and still wake up the same amount of people as we wake up with a much louder high-frequency alarm. So I had a couple of more examples here. This table is for older adults. Here are the charts for some of the other groups tested. Adults with mild to moderate hearing loss. You can see the red of the low frequency alarm, considerably better. Sober young adults, it's a little tighter, a little more questionable. The high frequency alarm performance is pretty flat through here. So there is a significant difference here, but it's questionable whether it's really better or about the same. But it's more significant, again, in these at-risk alcohol and slightly intoxicated groups. So 2010s, after all this research was summarized, published, it's pretty overwhelming. The evidence is pretty striking. We got to see some changes in our codes and standards. So 2010, see here, NFPA 72 included the requirements for that square wave. So not just requiring it in places, but defining what that square wave tone was. Having the odd harmonics, having it sound the way it sounds, and then requiring it in sleeping areas for notification appliances and for people who are hard of hearing. So that came into effect in 2014. In 2012, those low frequency requirements came into UL, defining the tone and the sound and requiring those devices in similar places in the building codes. So the problem here is, on one side, this is wonderful that we started to require this for people who are hard of hearing and for notification appliances, but there was a clear technology limitation. At the time, we couldn't really require this for single multiple station alarms in all sleeping areas. The reasons were mostly technological. Again, the power required to produce that sound, the size and weight of the devices required, and the cost of the devices was pretty onerous, especially compared to the existing piezo devices. So we weren't able to require it in those areas, mostly because we couldn't produce devices. We're still in a position where we can't produce those same devices. So the question arose at this time, could we reduce the sound pressure level of that low frequency and still get that same waking effectiveness? So this is when I got involved in 2020, kind of trying to answer that question. So I really don't want to bog you down too much in this, but basically I did all this background code analysis and justifications for the code, but I also went through 50 years of studies trying to wake people up with different tones, different conditions, and tried to come up with a way to compare them. So this is one study. You can kind of see that real basic curve. This is from 2014 on trying to wake people up on who've been taking sleeping pills. And you can also see here that 520 hertz signal, considerably more effective than the high frequency tone here. And even on people who took the sleeping pills, it's more effective than the people who didn't take sleeping pills with the high frequency. But you can see what I did here is I applied this EX over e to the x plus 1 function, which basically gives you this nice S shape. And you can play with X to kind of change where that curve falls and match different data sets. They all sort of follow this. Nobody wakes up. People start waking up. It gets real sharp, and then it flattens off as 100% of people wake up. So I tried to apply a function like this to every data set I could get my hands on, and then I could compare where I got 50% for a given alarm type at a given test at different frequencies. That's as much as I'm going to bog you down with that. But what this let me do is build this table where I could compare what did a high frequency alarm and what did the low frequency harmonic alarm do in direct comparison to each other over all of the studies we can look at. So again, you'll notice the population sizes for the low frequency alarm are much, much lower. I really only have about 5 or 6 studies from 2000 to 2015 really evaluating these, whereas I have about 60 years of all other waking experiments. But you can see how drastic the effect is for the at-risk populations, the ones we discussed. It's up to 20 decibels on average better than the high frequency alarm. So we already knew that that was better, but it's a pretty drastic number. If we look at every test and we average everybody out from all the populations, it's still about 9.1 decibels more effective. So we could be 9 decibels quieter and still be equal in performance. It's a lot more questionable over this normal population here, because if we have the tests in this row where I actually have the low frequency alarm and high frequency alarms, I have a really small sample size. But the low frequency alarms are about 6 decibels better, even among that normal population. If I take all of the studies over 60 years, where I've got hundreds of them for the normal population and only a few for the low frequency alarms, it may even be better with the high frequency alarms. There's a million reasons why that could be the case. 60 years of studies. Nobody was sensitive, everyone was sensitive to high beeping tones 50 years ago, but now we have 800 watches and phones and dishwashers and microwaves going off in our homes, so nobody hears that stuff anymore. But for whatever reason, it's either equal to a little improved over the normal population. So there's a whole other effect here that's not just waking effectiveness, and I may rush through this just quickly. This is the characteristic transmission of sound through partitions, so doors and walls. So this is how much sound is lost. So as this goes up and up and up, that means the sound is more muffled, more reduced by those partitions at higher frequencies. Whereas at lower frequencies, it travels through the wall pretty well. You even got this resonance controlled region where you've probably heard somebody playing bass in an apartment next door, and the whole walls buzz and rattle with the bass, but you're not hearing any of the treble come through the wall. That's basically what this effect is here. So when we're doing our engineering calculations, and this has even made its way into the SFP handbook for the last almost 40 years now, we actually apply a frequency effect when we're calculating the transport of sound. That's this constant C7, where at a 500 hertz tone, we don't apply any attenuation or reduced effect, but there's a 7 dBA reduction for 3000 hertz tones. So we already know that sound is going to travel better, even if they're installed outside in hallways or not in the bedrooms. This low frequency tone will travel better through your home. So this is actually a study evaluating that, also done by Doc Brook. And they put alarms in parts of the home, a full-size home, multiple floors, multiple bedrooms. The one I'm showing here is where the alarm is located in the hallway, and the measurement is made in a bedroom with a door closed in between. So a non-compliant installation, but how alarms may be installed in many homes, if they're lucky to have one in the hallway even, and how alarms used to be installed. So what you're looking at here is the number of, the percentage of the alarms that are audible given certain dBA thresholds. So the red being the low frequency and the blue being the high frequency. If we're talking about getting between 70 and 85 decibels at the bed for closed doors and hallway installations, it's almost impossible for the high frequency alarms here, and much, much more likely for the low frequency alarms. So if we even have them installed improperly, that sound still transports much, much better through doors and walls in homes and through furnishings at that low frequency tone. So a few more questions we can ask ourselves as we're looking at this, back to our original questions. So what was that basis for 85 decibels at 10 feet? Is it still really valid now that we're requiring alarms in all of the bedrooms and interconnected? I mean, this was the requirement when we were expecting them just in hallways. Why did we get rid of that 75 dBA exception in 1999? Likely to just prevent multiple devices and confusion at the consumer side, and not for any technical reason. Given alarms outside of bedrooms, is the 85 dBA even really enough to be alerting people? If we're going to assume they're going to be outside of a room anyway, do we even have enough for that? Was it even technically justified 40 years ago? So then why does this 520 hertz tone wake more people up? Is it the complex nature of it? It just sounds louder because it has more harmonic tones and your ear interprets it that way. Is there some impact of the A weighting that we're punishing this 500 hertz tone because of the way A rating is scaled? Is it the uniqueness of the tone and we're just desensitized to loud beeps compared to years ago? Is it the way we sleep? And can we reduce this low frequency tone? Is there enough justification here, given what we've looked at, or do we have to do more research and more study? Can we assume that the public's going to put them in right, or do we still have to design the devices like they're going to be in a hallway and not in bedrooms and not interconnected? And can we, if we even think that's the case, could we justify a reduction from the 85 dBA in the low frequencies? So a few discussion points we sort of brought up as a result of all this synthesis. It's really, really complicated to combine all these different studies. Human sleep, sound are really, really complex. And everything that we did over research over time just led to having to put the devices more places. You know, we said, all right, they're going to need to be in bedrooms because they're not working just in hallways. They're going to need to be interconnected because if the fire is in one bedroom, you're definitely not waking up in an adjacent one. We were not getting sufficient sound, and increasing the sound levels from the devices wasn't practical or even desirable, really. That 85 dBA at 10 feet had really been the same since 1967, except for that little exception. So is that still really justified? The installation requirements, we really want 70, 75 dBA at the pillow. This is proven insufficient for all these at-risk groups. Like, this hasn't worked for a lot of the at-risk populations. But we definitively see that the low frequency alarms were giving us a much better response for those populations. Not so much in the normal population, but it looks either equal or still better, even for the broader public. And we know that that tone is going to travel through walls and through doors and around a room better than the high frequency tone. So what happened? We did all this research in 2020. We actually changed the listing requirements for 217, 268. The consensus agreement of that technical panel was that a 6 dBA reduction from 85 to 79 was justified based on all this data and the research that had been done without doing additional work. So now low frequency alarms can use, that's 1/4 the power at 6 decibels reduction. So it's a lot less power requirement on those devices for the batteries and for the sounders. So the intent here was to make something, you know, technologically tenable for manufacturers. The requirements for where they go in 72, so sleeping areas on notification appliances and alarm, fire control panel devices, but not for single multiple station alarms. As the basis of this study, I actually didn't really recommend further research at the time. I didn't think that just doing more studies would really get us any farther. And the consensus panel agreed, made this change, and didn't really think we had to go study anything else at the time. Looking back on this 4 years later, there's actual products coming to market now. Nobody's ever really tested them. So it's probably worth bringing forward a study now and testing some of these real devices that have come to the market. In addition, we should really be looking at some of the life cycle. How much power do they consume? What kind of battery systems are reasonable? Is it possible to get 10-year sealed batteries in any of this, or is that just out of the question, even at the 79 dBA reduction? All right, I say thank you. I'm just in time for some questions here. Feel free to reach out, contact me, or I'll see any of you in Arizona in a few weeks. Looking forward to it. And I'll move on to questions.
Josh, this was just a great presentation. Lots of good information, and really spurred on some, I think, some provocative questions that we need to address. And we do have a couple that have come in, which I think are relevant. You did kind of answer some of these as we wrapped up, but I just want to touch base on them again. So one question was, are there gaps in the data that we need to be gathering, maybe that would support some of this future research?
So there's a lot we really didn't know, even at the time I put this really extensive literature review together. And the intent was, do we need a phase 2, which is usually how research foundation projects go, right? We figure out what we don't know, we do a gap analysis, And then we make recommendations for an actual test series to answer those questions. The evidence demonstrating the effectiveness was pretty much there. I just had to synthesize it in ways we hadn't really looked at it or compared it over time. And I think we were able to reach pretty good consensus. There's still a million questions you could ask and answer and try to quantify this better. But I really think if there's anything left to research, it's these new devices coming out. There's a few other questions that I've had come up. I fall asleep with AirPods in, and they have noise canceling, and my podcast turns off, but the earbuds are still in my ears. What does that do? I've talked to people who sleep with hearing protection aids in, the little orange foam pieces, and they have a certain spectral response to them. And that's never really been evaluated. So there are residual questions, but as far as making changes in building codes and NFPA 72, I think it's really just waiting on the development of the technology rather than us knowing more about it.
Great. No, I think that's kind of leads me to my next few questions. So under the current American with Disabilities Act for audibility, are there any gaps there that we need to mesh together, with the federal, regulations and the standards? Is that a gap that we haven't really dove too deep in yet?
I'm actually not sure the answer to that. I think the ADA would define what needs to be in public spaces, but I don't know that it's so specific about where people live. That's their home and where they can kind of define things. Maybe in some of the definitions of who qualifies as hard of hearing, and then, the low frequency would be required. I'm open to a better expert on the ADA than me to answer that, I would say.
No, just a question. So we talked about updating of the building codes, and with respect to physical placement of the alarms, when you talked about how much more effective the low frequency alarms are there new considerations now that meld into the typical placement on the ceiling, thought process of smoke alarms, and do we need to consider those, how close they need to be to those potential areas?
I think, as far as really general spacing, we've probably come as far as we can go. Every floor, every hallway, every bedroom. I guess there's some questions about what's a sleeping area, right? People fall asleep in their living rooms all the time. So requiring one physically in those areas. I think a study could probably be done on modern furnishings and the placement of alarms. In the 70s, people had these big, thick shag carpets and heavy piled drapes, and it's probably not as prevalent anymore, but we've gone building construction for a lot of sound isolation, right? Like the whole goal is not to hear the people in the room next door or on the floor above you. And that's not really how smoke alarms are thought of. So there may be some advice on placing them in certain locations in bedrooms to avoid kind of reflective interference, absorption by your curtains and carpets, but I don't know that anybody's going to go to that level.
No. So a couple of good questions come in, and I'll answer the first one here about the posting of the webinars. All of the webinars will be posted on IFC website, and you will, as a participant, receive an announcement with this particular webinar recording, and it should be available in the next 24 hours. But our next question is one that I actually was looking at also. So does the low battery alert on low frequency alarms also sound in the lower decibel versus the higher chirp? So what's that, physical sound? And this kind of goes to one of the questions I have about how do we train not just the public about this and educate them, but how do we train the fire service? I mean, the typical firefighter in the station is going to need an updating trainer, to say, okay, here's how smoke alarms work. They're the local resource, that the end user resource that gets tapped into all the time. So what steps do you think we should be taking in that area?
So I don't think any change in requirements have been made for the low battery chirp. I know I myself get very desensitized to it. You notice it for 2 days and then you stop, or it stops beeping in the middle of the night because the batteries get a little cold, and then they warm up in the morning and stops beeping. And I believe it was you the other day when we were preparing for all of this, mentioning, seeing an older woman who just didn't even know that it was chirping or beeping. So I think there's definitely some good logic behind changing that as well, but I don't think anybody's really pushing standards and changes. But I would expect, just from a manufacturing perspective, if you've put the low frequency sounder in, you're not going to add another piezo one to make the low frequency beep.
Yeah, so it's going to be the same device alerting the user.
I think it would come naturally without requirements.
Great.
As far as training goes, what can you say about educating the public? I bet 90% of people don't know the difference between the temporal 3 and the code 4 beep. That's not a smoke alarm, right? People hear a beep and they leave. So is it good to educate and have people start hearing the new sound and get on board with, this works better, and everybody, data shows it and we all feel great? Love it. Big education campaign. But expecting everybody to understand and recognize, I don't know. Is it likely? It's tricky.
No, I think these are just thought-provoking, concerns that may pop up that we, hopefully can provide a science to the house kind of, messaging on and give the right answer. So this has been a great presentation, Josh. So as we close up today, and before we close off, I just want to give you some last closing thoughts for our participants.
All right. Thanks so much.
So this ends our recording for today. And everyone will receive a email with a brief survey as we close out today. And then we are excited to let you know about the next event coming up. And this is a series of 4 webinars that are then going to be looked at and reviewed as part of the IFC National Home Builder Symposium at the Community Risk Reduction Conference. We've got a group of over 35 international and national attendees for that already. So I think we're going to get a lot of the right people in the right room to bring all this information together. And we look forward to seeing everyone in Glendale here. And I saw we had a participant from Glendale Fire Department. So Chief, I hope you're available to join us at the conference and take, in the specific experts. So on behalf of the International Association of Fire Chiefs, thank you for participating today. And we look forward to seeing you at our next event.